Hello and welcome to our presentation in the Duisburg RISC-V Group. Today we are talking about intelligent power modules and especially about an intelligent power module with RISC-V core in the context of our GaNext project. Intelligent power modules, also called IPMs, are used in various power electronics applications. Examples are power supply in computer centers, lighting, for example, in stadiums, tunnels and roads, and e-mobility, where IPMs can be used for motor control and also for charging electronics. A common requirement of these applications is an efficient converter. Overall, the electronics should become more efficient, smaller, lighter and cheaper. Therefore, the trend is towards higher integration of the components and also towards new materials such as silicon carbide and gallium-nitride instead of the conventional silicon. Voltage levels for IPMs are typically 600 volts or 1200 volts. Here is a picture of a commercially available IPM on PCB. It contains a controller IC, power devices and passive components. The controller is often also responsible for generating the triggering signals of the power devices, for example by PWM. The power devices can be MOSFETs, HEMTs or IGBTs. Gallium nitride or silicon carbide power devices stand out due to their very high switching frequencies. With voltages around 600 volts or higher, triggering these switches can be problematic. Therefore, adapted gate drivers or control circuits are required. In this IPM, the gate driver is also located in the controller IC. In our GaNext project, we want to implement an IPM based on gallium nitride HEMTs, which should be smaller, more compact and more efficient than conventional IPMs. For this purpose, 13 partners from the Netherlands, the United Kingdom and Germany are cooperating. GaNext is funded by Penta, a program for industry-driven research cooperation in the field of electronics. It was launched in February and has a term of about 3 years. The gallium nitride HEMTs are contributed by Cambridge GaN Devices. The gate drivers are contributed by Infineon. Fraunhofer IMS designs the controller IC in cooperation with Advico Microelectronics. The IPM layout is developed by the Technical University of Dortmund. The overall specifications are monitored by Catapult and the encapsulation of the assembled module is done by BESI. The finished and encapsulated module is provided to our 5 end users who commission the IPM in the most common applications: Lyra in charging electronics, Signify in lighting, Macon in motor control, the Eindhoven University of Technology in high-frequency converters, and Newways in photovoltaic inverters. Last but not least, Sumida contributes adapted magnetic components to optimize the performance of each application. Here is a schematic 3D image of the GaNext IPM. The heat spreaders are placed on top of the gallium nitride HEMTs. Positions of the controller IC and the gate driver under the encapsulation are indicated. The block diagram of the IPM is to represent the individual components and optimized functions in more detail. These are a tailored design of the gate driver, the intimate integration of the gallium nitride IC, a dedicated package with advanced heat extraction, integrated sensors in the gallium nitride IC for monitoring the operation area, and the control IC with integrated PWM and sophisticated safety features. We at Fraunhofer IMS are currently in the design phase of the controller IC, which covers a wide range of functions. Analog feedback signals regarding temperature, current and voltage, which are measured at the gallium nitride HEMTs, are processed. Furthermore, a high-resolution PWM, whose resolution should be much higher than the clock period, is generated to trigger the gate driver. The controller also contains complex regulators and filters for voltage regulation, which enable soft switching, cycle-by-cycle control, synchronization with other IPMs for multi-phase systems, and safety functions, for instance in case of fast load change or idle state. The RISC-V core is integrated in the bottom right corner of the chip. This chip can also be controlled by an external controller. However, an internal controller is advantageous for maximum integration. The internal controller must have sufficient performance for the filters and control tasks and a certain level of reliability.
The RISC-V implementation that we use for our embedded applications has evolved over the years. It was first derived from the V-scale implementation of the University of Berkeley in 2017 and was updated to the recent state of the specification in 2019. At that time, we also studied the design decisions of the RISC-V core done by ETH Zurich, and it included a few of them. In the meantime, we had developed a software stack for AI training and inference on resource-limited devices, which we also like to include some hardware support for in the core. For GaNext, the top priority design target is a minimum cost add-on to the control IC, because not all of the applications would require the processor to be integrated in the IPM. We also need to provide some level of fault tolerance and work in an extended temperature range due to the power dissipation in the IPM. Last, we need enough processing power to run the real-time regulation loops, either conventionally or with support of a local AI model. We therefore started with a simplistic three-stage pipeline design, including only an instruction fetch stage, a combined decode and execute stage, and a write-back stage. As the total core size would be determined by the memory size, we included support for compressed instructions in order to increase code density. We also decided to run the code directly out of a combined instruction and data memory without intermediate caches. The main tasks of the core in the IPM are the linearization of ADC results, the compensation of sensor responses, and the real-time filtering required for the regulation loops. This justifies the inclusion of a 5-cycle hardware multiplier and a hardware divider, thereby implementing the M extension of the ISA. We chose to implement extensions as coprocessors to the combined decode-execute stage using a simple interface called PCPI, as suggested by the PicoRV32 project. For large finite impulse response filters, and especially for AI inference, the speed of the hardware multiplier alone is insufficient. On the other hand, these operations do not require the full 32-bit accuracy of the M extension. We will therefore also implement a subset of the drafted DSP extension, especially functions on sets of 16-bit fixed point data packed into 32-bit words. We will reuse the multiplier hardware already present in the M extension though, which limits the introduced overhead. Some users will connect the IPM to an external controller, which can upload the required firmware to the control IC during startup. Other applications won't have this place to store non-volatile data, so we support code execution and data storage from an off-chip non-volatile SRAM connected to a quad SPI interface. The firmware routines that are continuously run during operation easily fit into a small amount of the on-chip SRAM when using the compressed instructions. So we decided to use an overlay approach where a software handler takes care to swap in and out of SRAM the required parts of the firmware. Although such a controller would be severely limited for general purpose applications, in our case this gets the job done and provides an optimum trade-off between chip cost and flexibility. Obviously, the core needs to control all the ADCs and muxes on the chip, and this is done using memory mapped registers. Same goes for the SPI interface to the outside world and for a synchronization block that has been used to operate multiple IPMs synchronously. For our design, we chose a mature 180 nanometers target process qualified for automotive use to account for the rough environment, including large reverse currents being injected into the bulk, strong electromagnetic interference, and an ambient temperature range from -40 to 125 degrees Celsius. We might also see a bit of self-heating of the control IC to about 150 degrees. The physical implementation results in a core size of 2 square millimeters, including the SRAM IP on the left. The maximum clock frequency is about 64 MHz, but we will clock the core at half that speed for better energy efficiency. The whole design uses junction-isolated standard cells, so there is a large isolated p-doped well underneath the digital logic that prevents the digital switching noise from being injected into the ADCs and the precision PWM. Running a torture firmware at full speed results in 30 milliwatts of power dissipation, with about 50% of the power consumed by the SRAMs. There is also something for us to do on the firmware side. First is to optimize our software library for AI inference and training to make full use of the resources we added to the processor. This will be done in a hardware-software co-design approach, which will determine the exact subset of the DSP extension we are about to implement. We also need to implement the overlay handler as part of our board support package. This has to be done in a robust way that is easy for the end users to integrate into their software development flow. And finally, the actual algorithms which in fact turn the IPM into a DC-DC converter, a PFC unit, or a motor driver need to be implemented. We are still investigating which level of redundancy and channel encoding needs to be implemented to account for the safety requirements we have. Lockstepping 2 cores will be only a last resort and serve as the benchmark for our more area-efficient approaches. The local training of a pre-trained AI model directly in the IPM is something we'd like to include as well. Although training is already possible with the current architecture, we'll look into including a training accelerator if it integrates well with the other extensions. Finally, some closing remarks on the importance of an open RISC-V ecosystem. We have been discussing topics like the European digital sovereignty for at least 5 years now. Meanwhile, NVIDIA has bought ARM, consolidating the market of technology providers even more, and the number of reports on hardware trojans, backdoors, and counterfeit chips are increasing. The Fraunhofer Society is hence discussing plans for a German trustworthy electronics platform with partners from the industry and the German government, and one cornerstone of this platform would be an infrastructure for the development of trustworthy SoCs based on RISC-V computing cores.
So thank you for your attention, and I will happily answer all your questions now.